This is the weekly hangout of LunarCubes, and today's event ID would be 140603. We have a very exciting speaker today, John Howitt of CSI MOOG, and also the co-host Mike Riley. So go ahead and Mike, say hello to the audience.
Hello, audience. This is Mike, coming from Rockville, Maryland. Happy to see everybody, or at least hear you. I'm going to be on video mute for most of this, since I have some background noise coming in, and I'm going to be flipping the slides for John today.
All right, now John.
Well, hello. This is John Howitt from MOOG CSA. We are coming from sunny Mountain View, California. I will have one of my colleagues in the office today as well, Joe Maley. We might not see his face, but he might pipe up and help us with the presentation today. I do hope that you find the presentation informative, and if so, please don't hesitate to contact me with further questions. Thank you.
All right, so we're going to move on to your presentation. And, John, go ahead.
Okay, thank you so much. So I'm here to talk about how we can make a more efficient, more sustainable approach to launching CubeSats and microsats beyond LEO and beyond the trajectory or orbit of primary launch vehicles slated on top of our rideshare opportunities. I do want to walk through a few design techniques that enable a more cost-effective solution, as well as the methodology for adapting this infrastructure to the to enable ride-specific or mission-specific manifests. I apologize, Abraham, I'm not seeing the slides right now.
Yeah, I'm seeing the slides all right.
Okay. Well then, thank you. So the objective of launch infrastructure, which is primarily what is required for our mission manifests, is to enable a budget-friendly transportation device that moves beyond LEO and moves to the moon or even beyond for the CubeSat community, while minimizing risk and offering flexible integration and launch opportunities. Really what we need to do is not be constrained to the launch schedule or launch integration process of the primary hosts or the big birds that allow the launches to occur. We need to enable our own mission manifests, and the infrastructure discussed in these slides will show one technique, and hopefully the best technique to move forward with that. We move to slide 2, please. I think there's somewhat of a lag. Perfect, thank you so much. So as this community is probably aware, one primary carrier for rideshare is the ESPA ring. This is EELV Secondary Payload Adapter. It was designed by CSA Engineering at the time, now MOOG CSA, as a method for relieving excess capacity of the EELV family, specifically at the time Atlas V and Delta IV. And what the Air Force realized is that their spacecraft, their primary spacecraft, were becoming smaller and smaller, and therefore the Delta IV and the Atlas V had excess capability. Along comes a secondary payload adapter, and where we could fit upwards of 180 kilograms, 6 payloads weighing 180 kilograms. Now, we'll talk about this later, but what happened is the primaries were worried about having secondary payloads. So the vision for ESPA has broadened. It is now classified as a highly configurable, adaptable architecture that enables all forms of rideshare opportunities for not only the small sat community, but also the micro, pico, and femtosat community. And there are ways to configure this ESPA to accommodate that. Along with that architecture, ESPA has been envisioned as a free flyer or propulsive device that allows these CubeSats to move beyond the trajectory of the primary spacecraft. And we'll talk about LCROSS and DSX a little bit. We move to slide 3, please. Another form, which has been conceived not for the EELV family, but for smaller launch vehicles, is the CubeStack wafer. Now, LoadPath, which is a private company working out of Albuquerque, New Mexico, was the primary for this effort, and MOOG CSA provided support in terms of adapter design and analysis. And this CubeStack wafer is a device that can hold multiple P-pods or other dispenser technology like the CSD from Planetary Systems Corporation. This adapter has flight heritage, most recently with ORS-3, where 28 CubeSats were launched. So what this is doing is stacking multiple wafers underneath the primary spacecraft and enabling high quantity of spacecraft to be launched during the mission. It's a stackable infrastructure so that you can, as seen in the upper left image, stack multiple wafers to deploy many, many CubeSats. Now, where I'm going with this is that the more wafers or the more infrastructure you provide for CubeSats and other launch vehicles, the cheaper the ride is per spacecraft to launch. So we're all looking for multiple organizations, multiple companies, multiple people looking to launch on the same date in order to minimize the cost and distribute the cost. So this CubeStack is designed around the 38.81 interface, which is most notable with the orbital launch vehicles, the former Taurus XL and Minotaur 1 and Minotaur 4. Okay, moving on to slide 4. Thank you. Now, beyond the primary infrastructure, which is the CubeStack wafer and the ESPA, we have other adapter hardware that allows multiple configurations for CubeSat deployment. One of which is the ESPA Sum, which is the ESPA 6U mount. What this does is interfaces primarily with the ESPA 15-inch port, but is also compatible with the other rideshare opportunities you see here. It was originally conceived for the ESPA port as an inboard or outboard configuration. And what this allows is we have a small sat sitting on the outside of one of these 15-inch ports. And if we have excess capacity, we could put an ESPA Sum on the inside and have 2 P-pods or a CSD or any other 6U dispenser interface inside the ESPA Sum to enable excess ride share on the mission. So the secondary would deploy from the ESPA port, and then tucked underneath would be the CubeSats that would deploy after the secondary has deployed. So again, another utilization of excess capacity for these big launch vehicles. If we move on to slide 5, please. Now, this is a game changer. This is another opportunity for the CubeSat community to reduce their launch costs and enable themselves to move forward and get onto any rocket potentially. This is a dispenser that's entitled Phantom Ride. Don't ask me what that acronym stands for, but it is a architecture envisioned by Tricept Corporation, and they recognized the need for launch infrastructure that would accommodate accelerated launch services. Specifically in the versioning microsat and CubeSat community, where these small launch vehicles necessitate flexibility in launch schedule, and also where primaries are unwilling to give that flexibility. Phantom Ride is completely transparent to the launch vehicle. What that means is these big birds, these big launch vehicles, want multiple rounds of coupled loads analysis. And if you're changing the architecture midstream or late in the game, late in the launch schedule, the launch vehicle providers are not happy, and they will not accommodate that. But what Phantom Ride does is provide a mass-tuned architecture that has the exact same dynamics regardless of the interior configuration, meaning the manifest of Phantom Ride, to be able to, even sitting in the integration facility, swap a satellite in for a mass simulator, or swap one satellite in for another satellite, so that the CubeSat community, generally with smaller budgets and not pinned down schedule, can come to the launch facility and put their spacecraft in for launch if the trajectory is right for them. So the Phantom Ride, it has the capacity to store up to 24 3U spacecraft or 12U, 12 6U spacecraft, and then incorporate a microsatellite in the center. It's a very, very capable technology that enables a whole host of rideshare opportunities. If we move on to slide 6, please. So right now we've talked about launch infrastructure that gets us to the same orbit as the primary launch vehicle. But most CubeSats don't necessarily want to go to that same orbit or same trajectory. We want to go beyond where the primaries are going, and we want to explore interplanetary space. So one way we do that is configure propulsion to these launch infrastructure technologies. We include propulsion on the ESPA ring, and we provide propulsion on the CubeStack wafer. And what this allows is, once the primary is where it needs to be, then we'll move on and provide orbit raising or trajectory changing capability with all these infrastructures tied to the different dispenser mechanism, infrastructure mechanisms, and get to where you want to go. So if we're going to the moon, we release the primary where it needs to go and then just keep trucking, and it allows for many different opportunities to get to these different locations. The moon, Lagrange points, Europa, Mars, anywhere you want to go. So we have envisioned propulsive ESPA, which in turn could be a orbit changer, but also a home base or a mothership, a communications hub that enables the CubeSats short-range communication, while ESPA can, or the ESPA mothership or home base can communicate back to planet Earth. So it's a novel solution that allows highly adaptable communications and rideshare opportunities, which is fantastic. The wafer adapter, CubeStack NLAS wafer adapter, is also can be augmented with a propulsive stage to get the wafers to the correct orbit that the community is looking to go to. If we move on to slide 7. And then one other idea which has been proposed and worked through with a very good group of team members is the ESPA Smart Carrier. This was developed as part of Omega, which is Orbiting Medium Explorer for Gravitational Astronomy. Uses the ESPA Grande, and it's not necessarily part of the CubeSat world, but it is a concept that is enabling for the CubeSat community as well. It has its own propulsion stage, and then each individual spacecraft that needs to communicate with ESPA also has small thrusters for precise station keeping. But the ESPA will get the spacecraft to pretty much where they need to go. So this is a concept envisioned specifically for what we're talking about in the LunarCube world. If we move on to slide 8. So how do we move forward? I think the biggest challenge that we've had so far is risk. You know, we don't have the accommodations in terms of schedule. We don't have the accommodations in terms of location or trajectory or destination, I should say. We don't have the flexibility in launch infrastructure. So we need to develop ways, and I think we have, to provide this flexibility to the CubeSat community in terms of adaptable configurations like the Phantom Ride, base infrastructure like ESPA and CubeStack Wafer. You know, further, we haven't gotten to where we wanted to go yet because procurement of launch vehicles is expensive. So we need to team up as a community, strengthen numbers. We need to move forward in that sense. We need to partner and pair up with other folks that are designing missions to these wonderful places and establish a community conversation that enables launches to these wonderful places in our solar system. So I hope that this presentation has been informative in terms of launch infrastructure and methodologies for moving forward with budget-friendly, flexible, alternative solutions to get to where we need to go. Thank you.
All right. That was a good one. And
yes, thank you for that. This is Russell.
Hi, Russell.
So Russell joined in, so say hi, and you can open up with the questions you might have, Russell.
So yeah, so this is Russell Cox, CEO of Flexion Engineering. Joined a little bit late, but yeah, I was glad to see you got the presentation off. I did a similar presentation on what we're calling the Lunar Arc, which is the ESPA ring to get you to L1. So I'm glad to see you've got this, the current thinking of MOOG as well as the current thinking we're doing as well. In terms of a question, to what extent is MOOG involved in finding the rides, or are you doing payload integration? What role does MOOG play?
Well, at the moment, we're designing the launch infrastructure solely, but we do communicate with multiple integration facilities, multiple brokers to distribute the knowledge of when launches are going up. We do not play an active role in brokering or providing integration.
Yep, thanks. Yeah, so that was the other aspect of that was so we're looking at the launches, and then we're looking at the kind of payload integration. I guess what I was going to say was I was in LA last week and talked to JPL, and JPL was pointing out that a lot of the communications problems are essentially solved or solvable, and also Space Launch SSL, which is Loral, Space Systems Loral, is talking about putting together a GTO platform, and so these concepts are beginning to mature and beginning to become available. And so part of what we're doing is with our Scientific Opportunities Workshop and other workshops is to go tell the science community that getting into deep space is no longer as hard as it used to be. And so I really like seeing your what you put together in your opportunities, and in the context of this special interest group and others, I look forward to pushing these ideas forward. Thanks.
Well, I do agree with you on that, Russell, that having multiple community members develop infrastructure and, as you said, a GTO stage from SSL, I think the last hurdle that we need to overcome is organizing the community in a sense that we can define a multi-manifest mission. We can get multiple CubeSat providers on board and multiple science missions on board. And right now there are opportunities like the Special Interest Group and the CubeSat workshop in April and iCubes that you just attended recently. I think there are these opportunities and these conversation pieces, but I think some of the conversation, some of the organization needs to be more focused towards not necessarily brokering, but how do we wrangle the community together more to fully understand key target launch dates and ensure that we have a number of folks that are willing to ride at those key launch dates.
Yeah, that's a big piece, and that's Pamela's special interest group is intended to wrangle together the scientists, and interestingly, that's kind of where we are, as the technical capabilities are far outpacing what the scientists are aware of, and so we're creating programs to go and explain to them that these opportunities exist. If they can put together a mission and a ride, we got the rides, we got the capabilities. So the engineering is becoming essentially a solved issue, but that's still pretty much news in the rest of the planetary science community. So we're trying to go spread the good word.
Agreed. I think that's wonderful. Yeah. So I think where MOOG CSA can be either heavily influential or play a big role is because we are being contracted to build this infrastructure, we can communicate more thoroughly with the rest of the CubeSat community.
Yep, great, thanks. By the way, as you just said it, I don't know if I missed that part in your presentation, but who actually is paid for this initial development? Is it MOOG or is it NASA, or how's this development created?
How about I say a combination of multiple entities, including ourselves?
Yeah.
Yes.
Yeah, no, that's good, and that's another aspect of this. Is a lot of people doing a lot of pieces from a lot of different directions, and it's all going to come together pretty quickly here, and so it's getting exciting. So thank you.
You're welcome. Yes, it's getting very exciting, and I think that we are hitting critical mass now, whereas the past 12 years have been slow progress, but with the ORS-3 launch last year, and then 2 days later with the Depner launch, and the Kibu module, I think I said that right, on the space. You know, we are definitely hitting critical mass here, and I think it's a fantastic time to be in this world.
Good. Thank you for that. Michael, you're back.
Yes. Do you mind if I pass the microphone over to Joe Maley, who has joined me in the office? He'd like
that'd be great.
A few words.
Yeah, just briefly, Russell. I sent an email out to Pamela last week about what we really at MOOG really need right now to help us understand if we can really provide this propulsive adapter hardware to get to the moon or beyond is a reference mission, like how many satellites to what orbit around the moon or on the moon or in the vicinity of the moon, and starting from GTO or GEO, whatever that is. If we had some reference mission, we could start sizing. We're doing this on a couple of other missions. One's a CubeSat and one's a larger small sat propulsive adapter scenarios, and we're trying to get some momentum here and maybe even write a white paper within the next month or so. It would be good if we had a reference mission from this group that we could do some sizing around, and it doesn't necessarily have to be one that's ready to go next month or anything like that. Yeah. If you could.
No, yeah. So thank you for that, and I saw that email, and so the basic reference mission is going to be from GTO to Lunar L1, and we'll get you more and more details, but this is what I just presented in LA, was this idea of the lunar arc. And
yeah, that using the mule, I call it the mule, but the lunar,
yeah, so the mule is ULA's idea, and there's lots of them, but the basic idea is a mule or an arc, some sort of carrier, and most likely the idea is the carrier is going to come from like GTO, and then you're going to sync up with the moon. You're going to go to L1, and then you're going to dispense a bunch of CubeSats from there. When we did the just kind of round numbers, it was as many as 100 pretty substantial CubeSats hypothetically could be fit in your bigger boxes. But we'll go figure out what those real numbers look like But that's the starting, because what's another thing I'll be talking with Abraham a little soon, and this particular SIG is going to work on, is it looks like when I was talking to Courtney at JPL, communications pretty much throughout cislunar space is sort of a solved problem. They can do it with radios. They can get you millimeter navigation and good communication throughout there. And what we want to do is look at laser. So the idea is you send the SVR ring to L1, you dispense your CubeSats at L1, and then what you have left behind is a communication node that can reach from L1 to L4 or 5, lunar L1, lunar L4 and 5, and lunar L2. So you could talk from Earth to the Moon, Earth to L1, to the 2 side lobes. You could basically reach everything you would ever need to reach and create a robust communication system with one really good communications node at L1. And so we'll talk about that as that's the reference mission we're going to go design. And it'll probably take us a little while, but by the time we get there in July for the survey meeting, we should have a good solid reference mission in place.
Looks good.
And I think that's perfect timing for you too, right?
Well, we're moving out like right now on a couple reference missions. We're trying to get something in the IEEE.
Yeah, and we'd certainly love to see what you guys are working on too. So if we all, it's a point behind the SIG. So you show us yours, we'll show you ours, and our goal is to get as many people thinking in this direction as we can.
Yeah.
Because,
Great.
There's a lot of stuff that people assume is hard is actually essentially solved. Like I said, when I was talking to JPL, they said you could communicate anywhere you want to, and you can navigate anywhere you want to in cislunar space down to the millimeter. And as far as they were concerned, of course, assuming you got a couple of $1 million per radio, it was a done problem. So now what we need to do is go beat down the prices, which has to do with flying more than once a decade.
Well, and again, I think beating down the prices is strength in numbers. Make sure that we have multiple people ready for a launch.
Absolutely. Yeah, that's going to be the trick, because even like the Space Systems or RAL system, the SSL thing, is you've got to combine everything into a 90 kilogram package or a 150 kilogram package. So this integration phase is kind of, so there are two thin spots I see. One is the scientists coming up with tens or hundreds of missions, which they don't have right now because it never dawned on them they could fly that often.
Or one mission with a constellation of 100 spacecraft.
Well, yeah, that's what I mean. Yeah, so that's the idea. And then the payload integration phase of coming together with four or five missions with 10 or 20 each. So yeah, that's. But we now have a lot more clarity, and like I said, as of this year, as of this week, I can tell you that a lot of things that people have told me couldn't be done 6 months ago or a year ago are actually pretty straightforward. So we got to go get the word out.
I have a question which extends the discussion in that direction. This is Mike again. The question I have is, what are some of the gaps that we see to realizing the vision of a multi-manifest mission? What are some of the gaps that we have before we can actually get to that, particularly with regard to launch schedules moving around and perhaps people wanting to postpone actual integration with one particular mission and swap into another? What are some of the gaps to realizing that sort of process?
Well, I think my opinion, and I'm open to answers from the community here. My opinion is that we have a lot of novel ideas. Excuse me. We have a number of novel ideas for missions and science experiments, but they aren't being implemented yet because of the roadblock of not knowing when a slot is available. So the hard part is the upfront cost of procuring a launch vehicle and launch services of that nature. Um, the gap is having the community understand that if we have enough missions signed up, we can go. So I'm not sure I'm answering your question quite right, Mike, but
Well, I think you raised the basic issue, and I would just kind of focus on a slightly different part of the funnel of saying that really it's the science missions, the demand side of 100 missions waiting to fly, and it's kind of like each of the three layers. There's the kind of the launch segment, the integration segment, and the science segment. And we're kind of in that realm where there's a little bit of each, but not enough of all of them. We need to turn that into a funnel. And from my point of view, that funnel begins with 100 science missions waiting to fly. If that happens, then the integrators will show up, and there's plenty of launch opportunities in principle, in the sense they're 20-some geosynchronous insertions. SSL talks about wanting to do 5 or 6 flights a year just for their part, and they only control about 25% of the market.
right.
So as the demand shows up, as the scientific opportunities and missions and capabilities show up, the stack of CubeSats, LunarCubes, deep space cubes that need to fly, once that pile of missions is available, the integration engineering piece will start filling in. So that's what we're going to be focused on this year and next, is really exciting and integrating the global science community, saying, you can build a 3U CubeSat, and once we got a stack of these on the deck, then we can get them flown.
Now, as we're all aware, the commercial side of things, or the commercial aspect of this world, always lags the science aspect. And us being engineers and scientists and tech geeks, for that matter, we definitely want to focus on the science world. But the true push, I think, will be in the commercial world, and somehow we need to identify commercial markets for these space applications that would enable a greater opportunity, a launch manifest opportunity.
Yeah, so we're looking at that, and one of the ideas is science pushes technology, and technology creates commercial.
Right.
And so again, it's this, why are we going to fly just to fly? Why are we going to fly just to explore? How do we push the envelope and make that useful? But that's, again, part of the whole structure of the SIGs and the workshops, is to tie that back in. In the end of the day, it all ends up having to become commercial by the time we're done. But yeah, this as we can start flying a lot of CubeSat missions, we can start pushing a lot of technologies, and we're not quite there yet, but the cusp is coming soon. I think within this year or next, we're going to see a real shift of a successful wave of CubeSat missions that's going to bring on the next phase. I got to jump off to my next call, but this is really great. So good work, guys. And Abraham, I'll talk to you later today or tomorrow. And Mike, good work. We got to talk as well. And Moog, thank you for presenting. Excellent work.
You're quite welcome.
Yeah, this is Abraham, and I have a question on the technical side. The typical reference configuration we're talking about, can you give a sense of what is the power package and the communication package likely to be?
I'm not sure I quite understand your question. You're asking how big or what the specs will be on these packages?
Exactly. So it's about the, if you take a couple of reference architectures or designs that you may have on the table, what's the typical power package look like? How many kilowatt or whatever, as well as in the communications package, how many bandwidth expected, and what kind of bands that you plan to use?
Well, that's a good question. I'm not well versed in that side of the technical world, but I think that we can definitely establish those requirements on a mission-specific basis. So if the community is looking for a certain type of power requirement or communications requirement, bandwidth opportunity, then we can manifest the mission to cater to those requirements. Unfortunately, I don't have any steadfast facts for you at this moment.
Okay, and I'm talking in the context of like when we are kind of going to continue to work on the ARC LunarCube 50
Yes.
that Russell is talking about. So it'll be nice if I have a base number to kind of work around. So if you happen to come across, please share with me. Otherwise, we'll kind of go from the ground up and figure out what would be a desired power as well as communication budget. Okay.
Okay. Yeah, and I think that's actually a good idea to pursue in the very near future. We can work with our other MOOG facilities that are well versed in those technologies and design more infrastructure in terms of communications and power that would enable this type of travel.
Excellent. Mike, you have any?
By infrastructure, you mean the ring itself and the different sorts of basic functionalities that it's providing?
Yes, that is correct. It's the hardware architecture that supports the I suppose the ride as well as the deployment of the multi-manifest mission. So really, we can also design in the communications, the avionics, the power management. We can also design in harnessing, so communications to the launch vehicle as well. We have a sequencer capability that's in development at this moment to command release mechanisms. But really, in the context of this discussion, I meant infrastructure as the physical mechanical hardware.
Very good. Just for the sake of previous experience and heritage, MOOG has participated or built its own upper stages before?
I would not classify this as an upper stage. No, we have not, technically. I think that in terms of terminology, I have not classified this as an upper stage. I think some other folks in the community have, and we're amenable to that, but I haven't called it an upper stage. Did that answer your question, Mike?
Yes, it does. It does answer my question.
Good.
And so, but it's still, you're approaching this like you're building a spacecraft.
Yeah, well, I would say that we provide the base architecture for integration. We don't necessarily perform the integration of the spacecraft.
That's
good to have.
That's right. Joe was saying not to say we can't, but we're not marketing it as such.
Yeah, excellent. That's very good overall capabilities to have in-house and still choose specific vendors if necessary. So that's a very good strategy, and it's quite comprehensive. And by the way, how many other divisions that you will be able to patch us into? Like MOOG seem to have quite a lot of capabilities built in.
That's right. So MOOG has what we call the Confederation of Capabilities, or the Federation of Capabilities, excuse me, and we can showcase almost every spacecraft architecture component, and then also assist in the payload development too. So if you name a spacecraft component that you need, you can find it in the MOOG catalog.
Okay. And if you don't mind, can you go back to one of the slides that you showed in the presentation? And I thought I could understand one notch more.
Sure, of course.
There were a pair of rings in one of those, like I think slide number 5.
Okay, I think Mike will be bringing that up shortly. Okay, so I see the ESPA sum slide. Is this the one that you were referring to, Abraham?
1 second. Well, just pardon me. Is that on the screen yet?
It is on Michael's screen, yes.
I think it's the next one. Maybe one more. One more. The picture on the right.
Yes.
Can you give a kind of scenario where what type of application that's intended for, like what its mission?
Yes, actually, this was a mission conceived for from a NASA concept to map our local planetary system, or the Earth system, gravitational fields and the interaction between the Moon and the Earth and other gravity influences like planets and the Sun. So the concept behind this is that the ESPA, as an upper stage, I suppose I'll use that term now, will distribute these 6 payloads into an orbit beyond the Moon, and have them tethered close to one another to map the gravity field, much as Grail did for the Moon, now on a much larger scale. And unfortunately, I don't know the science behind how they do this, but they have gradiometers in each of these 6 spacecraft communicating with one another and to map the gravity field of our local system.
Interesting. This Grande is the big version of the ring that I had seen in your facility?
That is correct. So the ring that we showed in the presentation was the standard ESPA, which is a 2 foot tall or 24 inches tall ring that is has the standard EELV interface, which is 1,575 millimeters, and then 15-inch port. So that's the standard. The Grande is designed as a 42-inch tall ring with 4 or 5 ports, and those port diameters are 24 inches. So it's one thing I should have mentioned during the presentation is that this ESPA ring is highly configurable to serve any mission needs. The standard ESPA, as shown in this slide, can accommodate 6 180 kilogram payloads, whereas the Grande can accommodate 4 or 5 400 kilogram payloads. So if that translates into CubeSats, that's a whole lot of CubeSats.
And when you stack them, how many typically make sense? Can you kind of stack 4, 5, 6?
Oh yeah, so it really is dependent on the customer needs. The Orbcomm Generation 2 launch that is scheduled for next week, next Friday, I believe, June 11th, will have 2 ESPA Grandes stacked on top of each other. And then the second launch of that same constellation will have 3 Grandes stacked on top of each other. So it really is dependent on what the launch vehicle capacity is to the orbit that you're trying to pursue, and how much space is inside the fairing, really. So I think I answered your question in the sense that we can stack as many as is required by the mission.
Excellent, excellent. Thank you for that.
Of course.
All right. And we're getting close to 10:45, and if we any other questions, we can kind of continue our discussion. Otherwise, we can close up for the day. So I just wanted to kind of check with you, as well as we should briefly touch base on what are our next steps that we need to follow up and continue the discussion, as well as specifying the reference architecture for the June target.
Fantastic. Well, thank you for having me, Abraham and Mike. I really appreciate the opportunity to chat with
I appreciate that too, John. And thank you for being on our Hangout. I look forward to continuing the discussion.
All right. If we don't have anything else, we can conclude for today and catch up with emails and other forms of follow-ups.
Okay. Thank you again.
Yes. Thank you.